Hello, everyone. I know the lunchtime coma could potentially cause some of you to fall asleep, so I'm going to use my wit to hopefully keep you awake. So today we have a bunch of systems that are increasingly complex and harder to manage. That's kind of why we all have jobs as SREs. If our jobs were simple, then computers would be doing them already for us. But there's a slight challenge, which is that in order to manage our complex systems, we need to have service level objectives and we need to have observability into our systems to understand how are our systems working, how can we repair them, how can we make them better. And the challenge is that observability tends to be a little bit expensive because in order to debug our systems, we need to have enough data to understand what's going on inside of them. What kind of data, may you ask? Well, there certainly are some kinds of data, like you can have data from your individual machines. You can have data coming from your end users. You can have log files. You can have metrics. You can have traces. And all of this just piles up and piles up. I think we need to basically categorize our data into two classes. We've got things that relate directly to user experiences, things that are triggered by your end users. And we have things that are host metrics, things that are properties of the systems that you're running that are not necessarily tied to the behavior of users. Most problems, though, are not per host, right? Most of the sophisticated problems that we deal with happen when you have corner cases, when you have interactions between components that didn't go the way that you expected, or where a user is doing something that you didn't quite expect, where you no longer can say, this host is misbehaving, I'm just going to restart it. Because if you could do that, then guess what? Your Kubernetes pod would have already gotten evicted from that host, right? Like, there are higher order problems that we need to look at beyond the per host metrics. Unfortunately, a lot of what we've done in our discipline has not really kept up. We instead need to think about how do we capture all of the full richness of the data that we need with the complete context that we need in order to debug what's happening inside of our systems. You kind of can't have an empty room and say, you know what, okay, there's this thing, it's in isolation, like I understand exactly what's happening, right? So this is the thing that Professor Leveson from MIT was telling us yesterday, right? Like, you cannot decompose your system and have any hope of understanding it. You have to look at the whole system in context. So what I'm going to argue to you today is I'm going to argue that user experiences in your system are very much like beautifully painted marbles, and that we need to take the same care with handling user data as you would take with beautifully crafted and painted marbles. By the way, these marbles were painted by my friend Emily Griffin. She's at Emily with Curls on Twitter. Go check that out. So our user experiences are like these beautifully painted marbles. Marbles have many different properties, right? They have a shape, they have a size, they have a color, they have a pattern, they have a weight, right? There are so many different properties of marbles. And each marble is singularly and uniquely different. I think we need to look at user experiences the same way. That the events in our systems all have these amazing properties, each of which is unique, right? Things like, which user is involved? Where did their data pass through? What browser were they using? What screen size was that browser? What's the request ID, right? When did this happen? How long did it take? These are all incredibly useful properties that can help us understand what's happening inside of our systems. We often, in the course of our jobs as SREs, have to answer questions that relate to how many or how much, right? We're often asked questions about the collection of events that have passed through our systems or the system metrics that have happened inside our systems. And yes, percentiles and distributions are kind of a variation of how many or how much. Because a percentile is basically asking, how many percent of events or marbles kind of fit below or above this classification criterion, right? Or when you're constructing a distribution, what you're saying is you're trying to group these things into categories by size or by weight. So how many of you have ever seen this game in a fairground or in maybe a vendor booth downstairs for a contest? How many of you have seen something like this? Guess how many marbles are in the jar? All right? Now, I could spend all day trying to win this game, right? If you let me unscrew the lid and take out every marble and count all of the marbles in the jar, right? I could do that. I could win the game that way. But I'd be sitting there all day counting marbles, right? I probably don't want to be doing that. And what about if I asked you to do something slightly different. Like, for instance, what if I asked you to count all of the yellow-colored marbles? Or figure out what's the most common color of the cat's eye pattern marbles? Or how many blue marbles are there that do not have a cat's eye pattern, right? We have to be able to answer not just simple questions like how many marbles are there, but more sophisticated questions. And we cannot spend all day doing this. So I think that this is a lot of parallels to how we debug our systems. Because we need to gather data about our systems and then be able to, without spending too much time or money, understand what's the count of events in our system, or what's the latency of events in our system that share these common properties. And we can't spend our entire budget on it. Our observability infrastructure cannot be the same size as our regular infrastructure, because then, like, you're doubling the cost of your infrastructure, right? You probably cannot run a profitable business that way. So here today, I'm going to tell you 3 strategies for how to deal with this spew of huge amounts of telemetry data. Here are the 3 strategies: reduce, reuse, recycle. I know this is a little cliche, right? Like, this is the thing that they tell you in environmental science, right? When they tell you as a kid, this is how we save the environment, right? Reduce, reuse, recycle. So let's talk about how this applies in the context of doing SRE. First of all, let's talk about reducing. Let's just store less data. Often, a lot of what we write tends to be things that are duplicate, or that wind up being meant to be readable by humans, but don't make sense at large scale when it's being read by computers, right? So let's go back to the marble analogy. Why is it that if I ask you to count all of the marbles with a color, why should I have to sift through all of the clear colored marbles, right? We don't need to insert into our systems additional gunk that has no relevance to the problem that we're trying to solve, right? We can just set that aside and not even put that into our system to begin with. We need to stop writing data that we're going to write once and read never, right? I think that we need to think about, how long do I actually need to retain this data for? How long do I need my debug logs for? Maybe I only need to keep my debug logs for 24 hours or 48 hours. I don't have to keep them forever. Additionally, we can think about structuring our data, right? I don't need to have the string, hey, by the way, hello world, inside of every log request that I write, or inside of every third log request that I write. Instead, we need to focus on reducing our logging data and structuring it to have well-defined fields that encode exactly the information that we need and no more. And that also makes it so that we don't have to sift through it when we're processing it, because we know what the format of that data is. Common formats for this include JSON logs, protocol buffers, right? Kind of anything that has a structure to it and has optional fields. Additionally, a lot of people write more than one event per transaction. And that results in you having to cobble through your logs and look for the 5 times that your event ID pops up in that log. We really don't need to do this. We can use a more sophisticated strategy of recording event data once and just buffering it and holding onto it until the end of the request, and then emitting all of the fields as one event or one marble. We don't have to have a collection of clear and colored marbles, right, like for one transaction. Just emit one. And if you have things that have a dependency pattern, we can use distributed tracing, right? We can say the parent of this event is this other event, right? And to have a trace ID so I know really quickly what things might have any relation to each other and what things have no relation to each other that I can discard right away. So this enables us to have a much easier view of how events flow through our systems without overwhelming our processing power. Unfortunately, trimming is not enough. Trimming often gets rid of a third or half of your bulk, but it doesn't reduce the problem of scale. If you're processing millions of requests per second, how do we deal with all of that data? The second approach that we need to take is reusing our data. We don't need to keep every single piece of our data if we can use some of it to stand in for other pieces of data by sampling it. So statistics can really come to our rescue here because it's a very well-trodden field, right? People do opinion polling of the public, right? People take small samples of the public in order to understand the wider behavior without having to survey every single person in the electorate to understand what they're thinking. The basic approach that we'll take here is that we need to count only a small fraction of events, right? If I have this entire jar of marbles, do I need to count every single marble in the jar? Or can I empty out like a quarter of the jar and count each marble in that set of a quarter of the jar and then multiply it by 4, right? That's the basic idea behind statistical sampling. Statistical sampling says when I receive an event, I'll roll a die. And let's say that my sampling probability is 1 in 6. So I'll count 1 in 6 of them and record details about that, and I'll throw out the other ones, knowing that eventually I'll see events that are similar to it later in the stack of marbles. And then afterwards I can say each thing that I recorded and collected represents n other. In this case, if I have a 1 in 6 probability, each individual event that I collected represents 6 other events that are statistically similar to it. When I have a trace, it's really important to think about how do I make sure that my traces are useful? Because if you have a small fraction of a trace or a fragment of a trace, if you're missing the things that came before it, or if you're missing some of the things that happened during it, it's less useful. So how can we deal with this problem of interrelated things that we may want to bucket together? Well, we don't have to independently roll whether or not we keep each event. Instead, we can look at something like the trace ID and say if the trace ID ends in a 0, I'm keeping it. Or you can say, I'm going to make a sampling decision at the beginning, and then I'm just going to pass that along with my trace ID in order to decide whether or not I'm keeping it or whether I'm discarding it. So what does this look like in practice? In practice, what this might look like is generating a random trace ID at the start of every request, and then propagating that trace ID along, and then making sure that we're looking at the end bits of the trace ID to make sure I know whether or not I'm keeping it. I also want to keep the sample rate, as I discussed earlier, because otherwise I don't know how many events that stands for. Don't be afraid of high sample rates. It is okay to sample 1 for 10,000 or 1 for 100 or 1 for 1,000,000, right? What's really important is that we need to make sure that we have enough values that remain after our sampling in order to be accurate, right? It doesn't matter so much whether there are 50 million people in your country or 300 million people in your country, as long as you've sampled at least 50 people if you're conducting an opinion poll, right? So the population size doesn't matter. The only thing that really matters is the variance in the population and the number of samples that we get, not the total number. And if you don't believe me about this, ask someone who's actually a professional data scientist. Joe Ross from SignalFX gave an amazing talk at Monorama Portland this year called Statistical Aspects of Distributed Tracing. And in this, he demonstrates that you can keep a very small fraction of the requests in a given timescale, and you can reconstruct almost identically the original data set when you multiply it by the weighted sample values if you collected them alongside. So if you collect your data carefully, statistically correctly, and with a little bit of bias, which I'll talk about later, then your inverse quantiles and your service level objectives will be safe under sampling. Heinrich is giving a talk about statistics for engineers, and you can catch that in discussion of this in the latter half of the workshop, so it's not too late to go over there at the end of my talk. What do I mean by an inverse quantile? So a quantile means that if you have if you're trying to compute the 99th percentile, right, that means that you're trying to find a numerical value that 99% of your samples will be below. Conversely, an inverse quantile says if I pick a threshold like 300 milliseconds, what percentage of events are going to fall under that threshold? Heinrich and I went back and forth on this, and it turns out that quantiles can be slightly inaccurate. However, the inverse quantiles are fairly stable under sampling. That if I know that, if I've counted meticulously everything in my data set, and I know that 99% of the things are under 300 milliseconds, if I sample 1 for 100 or 1 for 10, I can potentially wind up with something like 98.9 or 99.1% of values in my sample will be below that 300 millisecond threshold. So that's enough confidence to let us do our jobs. Is it exact? No, but it doesn't have to be, right? We need to know approximately what's going on inside of our systems, because the alternative is trying to be perfect and spending too much money on observability, or giving up and not having any data at all. Okay, so that's the second approach, which is sampling our data. Let's talk about the third approach, which is aggregating our data, which is recycling our data and crushing it. So how does this help us? Well, aggregation destroys cardinality. Aggregation at ingest time says, I need to compute in advance a certain set of properties about my data, and it removes all the other properties of that data alongside it. For instance, if I'm interested in the colors of my marbles in Aggregate, and how much by mass of every color there was, great, I can do that, right? I can go and stick the marbles into the grinder and go, right? Like I can grind up all the marbles and get marble dust. And I can separate it by color, and I can weigh it, right? So that's great, right? It's super cheap, right? Now I only have to track a few distinct values and a few distinct numbers associated with those values. Unfortunately, this is really mixed results because it's cheap to answer known queries, right? I'm optimizing for the questions I know how to ask in advance. For instance, knowing that I want to measure what the distinct mass is by color of my marbles, or what the distinct number of sizes is of the marbles without regard to their color. But where it really struggles is when we have to measure things that are combinations of these questions, or that are entirely new questions, right? If I've ground all my marbles into marble dust, I can no longer answer questions like how many blue cat's eyes were there, because the information about what's a cat's eye and what's not, that's been aggregated away. I no longer have it. Now you can add new custom series, right? You could say I actually do want to keep a count of how many color times pattern there are. But the problem with this is that most of the time, the values in that series might be 0 or small. And therefore, you're paying a lot more in overhead to store each distinct combination, rather than being able to encode it in a more simple fashion. So it's really inflexible, and if you try to make it more flexible, you wind up paying a lot of money that destroys the price advantage of doing aggregation. What you can do to try to reconstruct some of this data is to perform temporal correlation, right? If I'm grinding up marbles and I notice suddenly that I'm seeing more blue marbles, and my cat's eye detector is saying that, hey, I started detecting more cat's eyes at the same time, right? That might be a correlation, or it might not be, right? I might have suddenly gotten a bunch more cat's eyes of various colors and a bunch more blue marbles at the same time, and I don't know whether those are the same events or whether they're different events. Unfortunately, a lot of the solutions around this are trying to apply machine learning to a problem where the data has already been destroyed, right? And I think that goes to Todd Underwood's points from yesterday about the idea that you don't have enough data often to do machine learning, and you're just basically throwing darts trying to figure out, what does this vaguely look like? What you should actually be doing is actually collecting those full events and getting that full data. I want to talk about a couple of other pitfalls of doing aggregation. When you perform math on quantiles, it's really misleading. A lot of databases like Prometheus will wind up saying, I'm going to compute a 99th percentile value and give it to you as a scalar value, which is great, except for you look at the details. And what Prometheus might actually be doing under the hood might be computing the 99th percentile every minute. And you can kind of feel for, okay, this is the 99th percentile with n samples, and then my traffic spiked and it got slow, and now my 99th percentile is higher and I have more samples, right? But there's no way to kind of combine those quantiles after the fact. You can estimate, but it's not really good enough. The other thing that you can try to do is that you can construct histograms, right? You can say, these are the buckets of my histogram. And then you can say, okay, if I saw 10 total samples, 4 of which were below 50 milliseconds, 2 of which were between 50 and 60 milliseconds, and so on and so forth, right? I can guess where the median is based off of the number of samples that I saw. Or I can guess where the 99th percentile is based off of the samples that I saw, but I don't know where in that bucket they fall, because that data about where exactly in the bucket has been destroyed when I put the data into the bucket. So to me, aggregation is a last resort. When you cannot make any other method more economical, and you know what questions you intend to ask about it, then aggregation works fine. But aggregation fails when you're trying to understand attributes about your system that vary and have high cardinality. So you may be asking, great, Liz, you're asking me to do something that I cannot afford to do. But how do you make sampling cheap enough? So let's talk about how this actually applies in practice. So first of all, we want the cost of our observability infrastructure to be predictable. When you have data that is encoded in the form of time series, the time series more or less has the same cost over time, right? Because you're recording, a 0 sometimes, a 1 sometimes, a 5 sometimes, but you know how often am I pulling that data and what am I getting out? And what I'm getting out is like a 64-bit number every single time, right? So how do we make the cost of sampled events consistent over time? Our systems scale up in terms of their volume as they become more and more loaded. And we want to make sure that in the case of where you're paying for a fixed amount of retention, that we're getting a finite amount of days of retention, for instance. We need to make sure that the volume that I'm ingesting of events remains constant over time. And we need to make sure that we have enough data to debug, right? We need to make sure that we have enough representative traces of our system to be able to understand what's going on. But that doesn't mean that if I have a spike of 2x, that I also need to scale up the number of traces I'm collecting by 2x. What I can do instead is I can keep track of the volume that I received in the trailing minute, and then I can adjust my sample rate going forward for the next minute. So basically, this is what that might look like, right? I might look at how many requests am I receiving and make sure that I'm adjusting as I go along, and I'm making sure that I'm continuing to pass that sample rate along so that I know in the next minute when I've changed my sample rate from keeping 1 for 1 to keeping 1 for 2, that I know that even though I'm still sending 100 samples per second to my collection service, that I know that those stand for 200 requests per second rather than only 100 requests per second. So this enables us to keep a consistent number of events post-sampling, which keeps their costs predictable and low. And then we can reconcile and multiply it out by weighting by the sample rate on the back end. The other way that we can approach this and make sure that we have enough data to debug our systems is using per key sampling. 99% of the events that your telemetry is initially collecting are low in signal. They duplicate something that's not very interesting that you've seen before, been there, done that, don't want to do that again, right? It's just the math. If you're interested in the 99th percentile latency, that means you're interested in the 1% of events that are above that 99% latency. That means that everything that's below the threshold is not very interesting, right? Sure, you might want to keep a little bit of it so you can compare and contrast what's the difference between a slow and fast event, but you don't need 99 times as much data about the fast data as your slow data. Or similarly, what about if you're running a multi-tenant service? What about if you are running a service where you have hundreds of different clients with different orders of magnitude of traffic? I might care just as much about a client who's sending me 20 QPS as 20,000 QPS. But if I'm sampling naively and I'm trying to reduce the volume of samples I'm sending to 100 queries per second, that means that if I just naively take my total volume and divide it out, that I'm going to be sampling something like 1 for 100 requests, and I might only rarely catch some of these smaller customers. That's not okay, right? So my boss Charity says, nines don't matter if users aren't happy, right? If you have a customer that is 100% down, but it is so small that it's only 0.1% of your traffic, I bet that customer is going to be mad. But your dashboards probably are not going to show that. So how can we capture that? How can we make sure that we record enough data about our smaller customers as well? And that's all to say, how can we save the relevant events? How can we save the marbles that look completely different from all the other marbles? We need to normalize our sampling rates by key. We need to make sure that we allocate our budget of number of allowed events that we can keep post-sampling. And we need to make sure that it's allocated fairly across all of our distinct clients and across all of our distinct ranges of latency that we might have inside of our system. So if we have a different key, it can have a different probability that varies from all the other probabilities that we've seen inside of our system. So for instance, that client that's sending us 20,000 QPS of traffic, I might want to sample that 1 for 2,000 so that I'm getting 10 samples per second of that high volume traffic. But that client that's sending us 10 QPS of traffic, I might want to sample that 1 for 1 or 1 for 2, so I still get a few samples per second of it. This lets us go and allow those large customers to go loose with our system, knowing that we are capturing a statistically significant number of their events, so we can still understand the broader behavior patterns of their traffic, while not swamping these slow queries, the errors, and the rare customers that are so precious. So this is what this might look like, right? I might decide that if you are a slow query, or if you're an erroring query, I want to keep a lot of you, right? I want to keep every single slow query or every single error. If I'm only failing 1% of my traffic, right, it's cheap to me to keep all 1% of that traffic and then sample the 99% of my traffic 1 for 100, right? Then I'm keeping kind of 1 bad request and 1 good request at the same time. But how does this work, Liz? How does this work when you have a distributed service? How does this work when you don't know at the time that you initiate your trace whether or not it's going to succeed or fail? Because again, like, if I had the ability to predict in advance whether a query was going to succeed or fail, I'd be winning the lottery. I wouldn't be standing here, right? So buffering is required to allow us to choose wisely. And there are a variety of different solutions here, right? For instance, Lightstep has satellites that buffer traces for up to 5 minutes. Honeycomb does the same thing, right? Like, we have, the technology exists to keep your data for long enough to keep the entire trace and 100% of your traces, and then decide which ones look interesting, which ones took longer, which ones had an error somewhere downstream, and keep only those, and you can discard the rest, right? But you need to have the capability to hold on to that. Otherwise, you're making decisions only based off of what you know at the start of the trace, and not necessarily what you know at the completion of the trace. Okay, so let's put both of these techniques together. Let's put sampling things that are more interesting at higher rates together with sampling things and varying the rate over time. So what we can do is we can say, you know what, I'm going to maintain a count of events that I saw in each bucket, and then in my next time period, what I'm going to do is I'm going to use that sampling probability as 1 over the number of events that I saw multiplied by the target number of events per distinct key. And that way, I can have a variety of different keys that adjust with the volume of traffic. So I'm not, if that 20,000 QPS customer goes to 10,000 QPS and your 10 QPS customer goes to 1,000 QPS, right? You'll still get the approximate right ratios. It's okay for your client's rates to change over time. That low volume data is so, so precious because that's where the interesting properties of our system come from, right? They don't come from the queries that all look like each other. They come from the queries that look different, right? You want to understand and appreciate what makes them different. So when you put together target rate sampling and per key sampling, you get much better observability at a much lower cost. Some of you may be in metrics world, and that's okay. What I'm going to argue to you is that if you have aggregated metrics, what you have are a collection of distinct kind of ground up marble dust buckets, right? Based off of the time and based off of, for instance, size or latency, right? You kind of have relative volumes of data that fit into various bins. What an exemplar is, which I used to talk about when I worked at Google, right? An exemplar is when you say, for this individual bucket of marble dust, here's 1 marble that was fed into the machine, but here's 1 marble with all of its cardinality, right? So it kind of means that you don't have to keep each individual field of every single event. You can still get that aggregated count, but we're keeping some degree of properties of 1 representative event along with the amount of it that there was. So an exemplar is a distribution combined with sampled events from that distribution. But guess what I've been telling you? What I've been telling you is about the idea of sampling your events, multiplying them by a count. It turns out this is the exact same concept, that an exemplar attached to a distribution is the same as a sampled event with a probability that's been multiplied by. So metrics and events can be friends, right? The end limit of a metric system that has some cardinality is the exact same as the end limit of an event system that's been made affordable by sampling. You're collecting full cardinality data, and then you're using some of it as a representative sample, and you're discarding the rest. And this is how we prevent data spew. We prevent data spew by reducing, recycling, and reusing our data. So you can achieve SLOs and observability at sufficiently low cost if you apply a little bit of maths and statistics. So structure your data, get rid of all of that excess non-structured data, sample your data so that you get a representative sample, and if you desperately need to, aggregate by your known questions, but keep in mind you still might have unknown questions, so you still need that representative data in the form of an exemplar or a structured event. So hopefully that helps you win that guessing marble game in the future, whether it be at a fairground or whether it be inside of your systems that you're operating every single day. If you refine your data, then you can actually win and you can actually understand what's going inside of your systems. Thank you. Yeah, I can make questions.
Okay, we have time for a few questions.
There's a question right there.
Oh, sorry.
If you make debug logs into structured data, what's your opinion on having a general single field which has human readable values versus encouraging developers to make 100,000 distinct values, distinct fields, all of which will have a different meaning? And essentially will
it depends upon whether your system, let me repeat the question. The question as I understood it was, if you have a bunch of developers that are incentivized to create a number of distinct structured fields, then you're going to have out of control a number of distinct columns. So is it okay to have kind of a human readable column, right? That's literally just this is for random developer debug messages. So I think that it depends upon the behavior of your system. If your system tolerates null values and can run length encode null values, right, then it's okay to have many columns that are empty most of the time. However, it is also useful to have things like stack traces, right, things that are kind of, you'll see similarities in them pop up often enough that you can kind of group by that field and kind of see, okay, this is a number of distinct exceptions that have this message, right? So it's kind of this interesting balance. I think that you shouldn't throw like 1 megabyte of text into a structured log, right? But I think that shorter values are fine. I think that it's a question of, do you want to filter by this, right? If you have a failing user ID, you should have that user ID encoded in a column, right? The error message should not be conflated with the user ID because you might want to search for all the error messages that are being seen by that user ID. And if you have a column that is, a combination of some human readable text and then a user ID, you're not going to be able to easily fish out that user ID without running a full text grab. Does that help? Okay.
Okay. Oh, we have no.
So you talked about your approach of kind of this adaptive sampling and potentially propagation of sampling. So given existing protocols in place, and I guess what we're seeing with OpenTelemetry, do you see this as at this moment as a fully fledged feature you're trying to push for, or is it going to be something that we'll just put into baggage or trace space, whatever you want to call it for the time being?
Yes, so the question related to how does this work with OpenTelemetry? The answer is at the moment, OpenTelemetry does support encoding whether or not to keep a sample at the beginning of the trace. However, at the moment, OpenTelemetry does not have a good solution for propagating the sample rate, and I'm currently working on the OpenTelemetry standard in order to make sure that that is a standard part of propagation. So that if you are implementing sampling, right, if you're implementing sampling from the clients, right, then those sample rates are getting passed along. So that downstream, your span IDs also say, hey, by the way, this span stands for 9 samples or 100 samples, right? However, it's not strictly necessary, right, in that if you have a buffered sampling solution that can record all of the traces, that doesn't have to be implemented inside of OpenTelemetry. That just has to be implemented at the point that we take the full fidelity traces and full volume that we're ingesting, and then we send it upstream. Right, that doesn't require standards work. That just requires your proprietary or open source provider to do that sampling work itself and then record what sample rate it used. So I think it's a combination of those two things. I think we'll get there eventually. But right now, we've been so focused with OpenTelemetry on just getting the standard frozen so that we can get an alpha release out the door. That didn't make the initial alpha. I have full hopes that it'll be in that sample rate propagation will be in the beta by January.
Okay, thank you very much, Liz.
Thank you.